right, my physicist friends. I feel like it's been a very, very long time since we've had new physics content conversation. And it's nice to see you. I know that a couple people have already come up to ask me questions about grades and things like that. If you have questions about that, you can come see me at the end of the period or during Liberty time. That's totally fine. We can take a look at what's going on. I will tell you that I got a little bit lazy and overwhelmed at the end of the trimester. This is how reality goes. So there were some things that I did not have like graded in front of me, but I don't know if they got turned in or not. And I did not put zeros in there for you. So if you got lucky from that, you're welcome. Okay, I want to acknowledge that because it is a thing, and I apologize for that, for not being more on top of it. But for those of you that it helped out, there you go. I did go ahead and put corrections in from the trimester final. If you are not finished with corrections and you want to talk to me about that, then let's talk and let's have a conversation and figure out what the plan is going to be. And that is 100% fine with me. We are going to get started on unit, what is this, unit 8, I think that's right, if I'm remembering my numbers correctly. Unit 8, we've got unit 8 and unit 9, and that's all of the new content that we have. So we've got a couple of months, right? It's the 3rd of March, and our test is on the 7th of May, so that's 2 months. We're going to get the content done as efficiently, but also as in-depth as we can, okay? And then that'll give us a few weeks to do review before the AP exam, okay? So I just want to let you know that that's kind of where we're at on our trajectory. I don't have it all like mapped out to the day yet, but I will get there. And then know that after the AP exam, we will certainly do things that are related to physics, but my sense from last year when I talked to students after the AP exam and we were doing these things, that they enjoyed them, that it was good physics, but it was not like super intense, like listen to Ms. Carveling teach you stuff about physics. Okay, so hopefully that you will find that as well. Okay, today we are starting the unit that will be uniform circular motion, gravity, electricity. It's got a lot of little pieces in it, and I really like it. Okay, do you guys have any questions before we jump in and get started today? That rotational acceleration lab that we still have not gone over, we will go over it. I just didn't want to jump into it today. And the data that you took on Thursday with the stopper swinging over your head, we will get back to that. We're actually going to do our lab analysis with that on Friday. We just don't have the physics background yet, but we'll get there between today and Friday. Okay. Why don't you please pull out your notes, okay, because we're going to jump in. We've got a warm-up problem to get started with, and then we'll just go. We're just going to make it a good day, all right? So here is a large version of that same question. It's a ranking task, not from the ranking task people, though, from a textbook that I found, I don't know, a million years ago or something. It says rank in order from largest to smallest the period of the motion of the particles A to D, okay? This might take a little thinking. This is going to be about as much as we refer to the rotational motion from last unit as we will do, but I'm going to go ahead and give you a couple of minutes to think about this, to get your brains back in physics mode and thinking about what is going on. All right, my friends, let's discuss. Are you ready to share some answers with me to start? Yeah, show me what you got on your board. Let me see. Okay, so I see, whoa, that's in bright blue. Let's change that to something else. How about red? Yeah, it's kind of weird looking, right? So hold on, keep them up there so I can see. C is greater than A equals, D is greater than B, C is greater than D, greater than A, greater than B, ADB. I saw another one. Oh. She's like holding it upside down. It was adorable. Okay. Okay. Oh, you guys are same thing. Okay, got you. Okay, so we had 2 different answers. And as you know, just having an answer doesn't really give me very much information. I need to know why you advocate for one or the other whatever. So somebody help me out. Go, Chris.
So you know that he's going to do this. He's got the largest diameter, the largest circumference.
Okay. So hold on just a second. Let me write this down because I just want to make sure you've got this. So you're saying the largest radius or diameter, so that means the largest circumference? Okay. Smallest velocity, which means what did you say? Longest amount of time. Okay, now everybody agreed that C was the biggest. So then things get a little bit dicey here, right? So talk to me about why A and D are either D bigger than A or D equal to A. And it can be Chris or it can be somebody else. How did you come up with that? Go ahead, Emma. So A's got a V and an R, and D has got a 2V and a 2R. Okay. This seems reasonable. Do you have physics to back that up, though? Like, can you tell me exactly why that's true? Because I agree that it makes sense. But you have to be careful on these ranking things, right? To make sure that it's not that like there's something that has got a squared in it, right? Because if something has a squared in it or like a, you know, I'm multiplying by something, then it might throw things off. Josh? Okay. Okay. Okay, how'd you figure that out? Gives you seconds, right? Yeah. I'm going to take it one other way, but that's like units. If you don't know what to do, units always tell you what to do, right? Units always guide your thinking. One of the things that we're given there is velocity. What is velocity from like August, September, maybe? Distance over time, right? In the time of one cycle, what is that called? Time of one cycle would be the period. I'm just taking this back to make sure that everybody's feeling okay. How far does it go? One time around, or the circumference 2 pi r. Do you have to have this written down? No. But I want to make sure that when you're doing things like this, when you're doing ranking, that you feel like you really understand it. And it's not just like, oh, that one just looks like it should be better. Because you have to make sure that there's no, like, again, no squareds, no funky stuff that's going on, addition or whatever like that. If I solve this for t, which is I think what Josh was saying, we got 2 pi r divided by v, units, right? Just units, because this is meters and this is meters per second. And so if you do meters divided by meters per second, that just gives you those seconds. Yeah. And so if you double this and you double this, then your period's going to be the same, which is what was being said here about the orange stuff, right? And then little b has got a really big velocity, but a radius that's the same size. Yeah. So I think it's this guy here. But again, I want to make sure that you understand why that's actually true. How are we doing? Okay? Go ahead and erase that board. We're in a new little spot in your notes. Okay? We are going to start a unit or a part of a unit called uniform circular motion. And before we define it, we're just going to do a little like reminder of some physics from a long time ago. All right. So we'll start this one. Draw free body diagram. You ready? Oh, I love free body diagrams. Remember free body diagrams, right? All the forces acting on one thing. I got this thing. It's a cup. and the cup is being held up by some strings, you can assume that all those strings are just one string. Okay, it is Diego. Yeah, he's hanging out with some sea turtles, I think. Yeah, it's pretty fun. Yeah. All right. What I would like you to do right now is to draw a free body diagram of the cup. Can you do that? Great. Go ahead and do that real quick. And once you've done that, you've got one on your paper, then have a quick conversation and draw a free body diagram on your board. One per pair or trio. Okay. You've got a cup. And it's on some strings. I'm just going to draw it as one string. Okay. Again, once you think you've got it, then check with your table mates. Draw a free body diagram on your whiteboard, please. Show me your boards. Show me your boards. Looks like I've got 2 forces. Cool. So just to note, we've said this before, but I just want to remind you, because we have to like get into really good habits and practicing well. Oh, I am. Thank you, Fred. When you're drawing a free body diagram, generally you're going to draw it from a point, right? On an AP exam, it's just going to have a point. That is the center of mass of the system. Does that make sense? Your system is whatever it is, and this one's the cup, right? So the center of mass of the system, what forces are acting on the center of mass of the system? Let's see. Maddie, can you give me one of the forces acting? The string. Which way does that one pull or push? It goes up, right? So we're going to just go ahead and draw that. And a friendly reminder, so I'm just going to write this first, force of the string on the cup. And what kind of force is that? Tension force, FT. It's really, really important when you're doing a free body diagram on an AP exam that your arrow touches the dot. Have I told you this? Yes, because if it doesn't, you don't get credit. It's goofy. They just had to make a decision, and that's the decision they made. So yeah, it's got to go just like that. All right, that's one force. Jason, do you have another force on your free body diagram? Force of gravity, which is the force of the earth, absolutely, on the cup. And which way does that one go? Goes down. All right. Hey, quick question. How does this force compare to this force in size? They're equal in magnitude. How does it compare in direction? They're opposite. Are these a Newton's third law pair? Oh, that's a good question, Ms. Carveling. Thanks for asking. Thanks for reminding me. Is this a Newton's third law pair? I don't remember. That's been a long time since we've talked about that. Do you remember Newton's third law? No, so long ago. This was Alice and Boris, and they were ice dancing. Remember? And they push off. The force of Alice on Boris equals the force of Boris on Alice. That's a Newton's third law pair. Binder on table, table on binder. That's a third law pair. Right? Right? Is this a third law pair? No. What's the third law pair that goes with earth on cup? Cup on earth. They're the same magnitude, opposite direction. That's a Newton's third law pair. You will never, ever, ever have a Newton's third law pair in a free body diagram. Okay? Just a nice friendly reminder. That's not what we're really doing today. I just want to remind you of that. All right. Issues, questions, or concerns here? Okay. They're equal in magnitude. Wait, how did you know that? It's not accelerating. Yeah. Okay, good job. Okay. Good job. All right. Now we are going to, I need a volunteer. Who's that volunteer going to be? Eliana, come here. I know you were. So just to clarify what we're doing here, friends, we are going to draw, or you are going to draw, a free body diagram of the cup up at the top here. Okay, so here is the center of mass of the cup water system. The string was down like this. Okay, and I would like for you to draw that free body diagram. Go ahead and do that on your whiteboard now. I'll give you just a minute or two to work on that. All right, so we're going to look at these boards, and I want you to engage in this. And I don't want you to just assume, oh, I got it, or oh, I didn't get it. I want you to figure out which one this is. I'm going to actually turn this on. There we go, so that we can see. All right, so we've got it looks like all of the free body diagrams have an FG on them. Does everybody agree that the force of the earth is pulling on the cup and water system? And it's pulling which way? Down. Okay, so good for us. Nice job. Yay. Okay, let's see if there's anything else that's similar. Do you see any other similar things on these free body diagrams? Right, but I'm looking for things that are the same on all of them. I think string, T, 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 T. Yes, it looks like they all have got a string. And which way is the string pulling? Down. So I'm gonna pause for just a minute here, and I'm gonna bring this back so that we can write these down, because I think based on what you have on your pictures here, you all agree that those forces exist. Is that true? One little note in terms of AP testing is that you need to make sure that you've got both of those forces there. So we've got the earth pulling down, and usually these dots are a little bit bigger. We got the earth pulling down here, the force of the earth on the system, FG. And you've also got tension, and we agreed that it's going down, so I'm going to pull it like this. And we don't necessarily know how these two compare in terms of size. I think that the earth on the system here and the earth on the system down here are going to be the same. Would you agree? Okay, but up here, I don't know how that tension compares. We're just gonna go ahead and draw it there. And I also am going to write, this is the F of the string on the system, FT. And I think it's fair to say that both of these are definitely pulling or pushing. Now, on some of these boards, we have other things going on. So let's take a look and see what those other things are. So it looks like on this one, it says F question mark on the system. So we were trying to have a relationship between our system and something, because a force, thinking way back to like October, a force has to be a relationship between how many objects? Two. And it's always two objects, right? Always an interaction between two objects. So force of something, but whichever group said this, they're like, I guess I don't know what that thing is. Something's got to be pulling this way. This one says force of the water on the cup. So I get that, although I think that we had said that the cup and the water are a system together. Does that make sense? So if the cup and the water are a system together, that would be an internal force between that system. And so I think we'd leave that one off. Is that okay? Could I like maybe put a line through that? Okay. And then this one also says the force of, I think, marbling on the cup. So that would mean that while this thing is going around, I just want you to kind of think about what's going on here. That would mean that while it's going around, I am literally pushing on the cup this way. Now, again, I'm not a magician. I want to make that very clear. But as I was swinging that thing over Alana's head, Alana, did I have my hand up here pushing on it like this? No, I didn't. So I'm not pushing on it in that direction. Does that make sense? So that I don't think that that actually fits there. I'm not saying that this is right or wrong. I just can't think of what that would be. Here, so it looks like this group wanted there to just be a force, right? And Chris, you had made an observation that most of these have this thing to the side, right? So FA, and this one says FA. This one says F carbling, but we agree that I was not pushing on it. Oh, this one's got a question mark, so it's like force of question mark, right? So these are kind of, oh, that one's a question mark that way. And some, force of X, Y, Z. Woo, I don't know what X, Y, Z is. Do you guys know what X, Y is? Is that like some sort of secret something? I don't know. Thank you. Okay. So again, we have to remember that anything that's actually applying a force has to be a force of blank on blank, object on object. Alana, I'm not going to make you come up here and do this again, but I just want to imagine that Alana's sitting here, and I put water in the cup, and I'm doing this. Is there anything else pulling or pushing on the cup when it's up here, besides the string pulling down and the earth pulling down? The air would be pushing in all directions, so let's not go there. Did you say the gravity of the sun? Oh, yes, but we could do the math to make the argument that all of those forces are very, very, very small. In fact, my friends, and this feels really strange, I can't think of anything else that's pulling or pushing on the water cup system up here. I can't think that there's nothing else. There's no like other strings attached. There's no other, normal forces or anything. Like there's nothing else pulling or pushing up here besides the string and the earth. Now I tell you that, and from an academic, like reasonable person sort of way, like, well, sure, of course, hey, that's true. My question for you is, though, if those are the only two forces acting, why did almost all of you want more forces acting?
It doesn't make sense.
Okay, there were lots of answers. So I'm just going to go for, what'd you say? It's going in a circle. Sure. Yeah. Lucy, did you say something? You said something a second ago. It does, yes. Right? That's weird. That is super weird. Let's write our F-net equation for the cup water system at the top. Let's do that. It's weird, you guys. F-net at the top, we've got Ft, and that one's negative because it's pushing down. And we've got Fg, and that one's negative because it's pushing down. And if I have two negative numbers, are those going to add up to 0? No, in fact, they're going to add up to something negative, right? Which means that this stuff should be accelerating. That water and cup should be accelerating. Question for you, is it? Say again? What'd you say? What do you mean it's accelerating? Or how do you know it's accelerating? Uh-huh. Yeah, I love that. That was awesome. Friends, what does it mean to accelerate? Think way back to like, I don't know, the 3rd day of school. What does acceleration mean? It means change in velocity over time, right? What does it mean to change your velocity? Speed up or what? Say aloud. Yeah. This was a long time ago, you guys, but we talked about the difference between speed and velocity. Do you remember that? Speed is just how fast you're going. Velocity includes direction. And everything we've talked about up till now, through Save That unit that we just did, was talking about things speeding up or slowing down. And I told you, probably if you go back in the videos, you would find that someone is like, oh yeah, and someday we'll talk about direction. That's today, we made it, oh my gosh. If you watch this cup, whoa, hello, little monster wanted to steal it, I guess. If you watch this cup at the very top, if I'm moving it at a constant speed, that's a loaded question. If I'm moving it at a constant speed, is it speeding up? Is it slowing down? No, but if you watch the cup water system at the very top, is it changing direction? For sure it is. If I take this cup water system and I'm spinning it, and at the very top, so we just like freeze frame right there, and I cut this, so I'm spinning it like this. If I cut the strings, where is that thing gonna go? Is it gonna immediately fall down? No, that's fine. I'm not gonna cut the strings because I like this little thing, but I'm gonna do it and I'll just let go. That sound okay? So I want you to watch carefully. Here we go. We're gonna see if I can do this so I can time it at the right. I don't feel like I've got enough confidence to let go at the right time. Here we go. 1, 2, 3, go. Where'd it go? Right? That's interesting. That's interesting. So like if we think about this, I'm gonna draw a picture down a little bit lower because I feel like that's kind of convoluted up there. But if I've got my object here and it's going around in a circle, that's supposed to be a circle. My circles are not perfect, but there we go. Something like that. At this very moment, at the very top, tell me about its velocity. It's not constant. But which direction is it going in? It's going around this way. Where is that thing going to go? It's going to go to the right. It's got a velocity in this direction. It's got a velocity in this direction. If you look, and you probably didn't even think anything of it, but if we look back at the pictures that we did in the warm-up problem, did you notice that all of these velocities go directly away from, do you see what I'm saying? Yeah, they don't go in or out. The velocity is this way. The velocity is at a what kind of angle to the radius? A right angle, a perpendicular angle, or whatever you want to call it. There's a T word that means that. What is it? Tangent, tangent, tangent. She's so excited. Tangent, tangent. Yes. This right here is what we call the tangential velocity. Okay? The tangential velocity of the object. We're going to back ourselves up again. This is like, I love doing this unit now because we get to talk about a lot of things that we haven't done for quite a while. That's supposed to be exactly perpendicular. It does not look perpendicular. I'm going to draw it again because it's going to drive me nuts otherwise. Let me try again. Come on. Is that better? I feel like that's a little bit better. Okay. So the game is, do you remember Newton's first and second law? Do you remember that? Was a long time ago. We probably studied it for the final. Oh yeah, that thing. It was the if. Yeah, I was going to do it in the nice happy way. If F net is equal to 0, what happens to the acceleration? It's 0. That's Newton's first law. If F net is not 0, what's going to happen to the acceleration? It's not 0. This is where you get F or A is equal to F net over M. But really, this is the part that I care about. Is the net force on this cup water system 0 at the very top? No, it's Ft plus Fg, right? It's not 0, which means there's got to be some acceleration. If there were no tension force, this object is going to go, right? And in the situation that we're doing, then it would experience projectile motion, right? Because if you put the floor, I'm just going to draw this because it just kind of makes my heart happy, kind of all goes together, right? That'd be just a nice little projectile. Yeah? Yeah, it's all coming back. This thing right here, though, this tangential velocity is what would happen if the object could go in a straight line, if there were no forces acting. But instead of being able to go in this straight line, what's pulling on it? The string. So the object is up there. It wants to go in that straight line like the orange thing shows, but the string's like, not so much, friend. You're going to be here. Okay? And then at this point, it wants to go like this. But can it? No. The string says, not so much. You're going to go over here. And then it's going to go this way, and it's just going to keep going. So there's this thing, this force, that keeps pulling it which way? In towards the center. This circular motion stuff, okay? This circular motion is due to a net force, okay, that pulls the object toward the center of the circle, okay? We could also say then that if it's pulling the object towards the center of the circle, it's got a center seeking acceleration, because wherever the net force pulls, the acceleration is going to go, right? And Chris, I'm going to trust you here to answer this question carefully. A center seeking acceleration is also known as what? As a centripetal acceleration. Yeah, nicely done. Nope, don't do that yet. Okay. So I promised Ira that I would answer the question that he wanted to know before the bell rings, and I've got 2 minutes, so I need you to listen carefully. So Chris keeps pushing my buttons by saying a word that's not okay, and I need to explain to you why. Okay? How many of you have ridden or have ridden the silly silo at Adventureland? Does anybody know what that is? You go in a circle. So for those of you that haven't, I'm gonna do this really fast so that you know what's going on. So there's this room. It's a big cylinder. It's like walking into a Pringles can. You stand there. Don't put yourself away. Just listen for just a moment because I want your ears and your eyes and your brain with me. Okay? You walk in this Pringles can and you stand there and you're waving at your friends on the other side. Then it starts to spin. Okay? So you are moving in circular motion. And eventually you start moving at a constant speed. It's really just uniform circular motion. And it feels like what? What does it feel like? It feels like there's somebody going like this and like pushing on you, right? Pushing you away from the center. But is there anybody pushing you away from the center? No. In fact, if some evil, mean person decided to snap their fingers and the Pringles can, like that got rid of, where are you gonna go? Then you will go tangent to the circle. You have a center seeking force that's keeping you in. None of this center fleeing business. It doesn't exist. We'll talk about it more tomorrow. Have a great day, you guys. It doesn't exist, which is why we don't say it. But what, Emma? I know. Well,